Wireless networks are computer networks that are not connected by cables of any kind. The use of a wireless network enables enterprises to avoid the costly process of introducing cables into buildings or as a connection between different equipment locations. Wireless communications have many advantages, starting with the fact that you don't need to buy and install cables. If you ever try to bring your television from one room to another, you know how much effort it will take. Now consider trying to do this for an entire building that is constructed before computer networks even existed. Wireless communication used electromagnetic or EM waves that travel through the air. The simplest example of this will be the old-fashioned radio. Driving in your car, you can turn on your radio tune into your favorite radio station and listen to some tunes. You are receiving radio waves, which is one type of electromagnetic waves. Electromagnetic waves are analog, while the information in the computer is digital. Wireless networks therefore needs adapters and routers to translate between analog waves and digital signals. Wireless communication systems can be broken down into three broad categories: short-range wireless communication, medium-range wireless communication, and wide-area wireless communication. Short-range wireless communication uses signals that travel short distances from a few centimeters to several meters. Examples include Bluetooth, infrared, and Zigbee. Medium-range wireless communication uses signal that can travel up to 100 meters or so. The most widely used type is wireless fidelity or Wi-Fi. Wide area wireless communication uses signal that travel quite far from several kilometers to several thousand kilometers. Examples include cellular communication and satellite communication. There are many different devices that uses one or more of these wireless communication systems. One of these is the mobile phone or cellular phone. For 2017, the number of mobile phone users is forecast to reach 4.77 billion. That is more than have access to clean drinking water. A mobile phone is an electronic device to make and receive phone calls over a radio link while moving through an area. The primary wireless connection for a mobile phone is the cellular network that uses cell towers for the transmission between mobile phones and the network. A mobile phone is also referred to as cellular phone or simply cell phone. The earliest commercial mobile phones date back to the 1980s, but it was not until the 1990s that they became widely used. Modern mobile phones are not only used to make telephone calls, but also provide text messaging, email, internet access, as well as the integration with other devices. They can also be used to take pictures, watch movies, and play games. Mobile phones with these capabilities are referred to as smartphones. Smartphones are essentially mobile computers. They provide file storage, have a number of input and output options, make use of an operating system, and allow you to run applications. Relative to regular desktop and laptop computers, however, they are much smaller, often lack a physical keyboard, and rely on touchscreen technology for user input instead of a keyboard and mouse. Most smartphones can also use the other wireless communication systems, such as Wi-Fi and Bluetooth. These have made them even more versatile. For example, you can make hands-free calls in your car using a Bluetooth connection, or you can connect to the internet using Wi-Fi to make video calls. Have you ever wondered how a cell phone call works? As simple as it may seem, there's a lot that happens between the moment you hit call and when your friend picks up. To start, the city is divided up into a series of cells Base stations provide the cell with the network coverage which can be used for transmission of voice, data, and others. When joined together, this cell provides radio coverage over a wide geographic area that allows large number of portable transceivers to communicate with each other even if some of the transceivers are moving through more than one cell during transmission. Essentially, the radio towers overlap to cover a large area, so as you move around the city, this overlapping activity keeps you connected at all times. When you make a call, your mobile phone sends and receives radio signal, also known as radio frequency fields. The antenna of the nearest base station receives this radio signal, and the base station then forwards the signal to a mobile telephone switching office. The MTSO connects the call to its destination, either a fixed line or mobile phone. This is to ensure that the mobile phones maintain the link with the network as users move from one cell to another. The main purpose of cellular network providers is to provide network reliability and coverage. However, there are still factors that affect the connection regardless of the carriers, things like tunnels and mountains, building materials like ladder and thick concrete walls, or other nearby power sources. Filipinos usually associate traffic with the long postponement in a certain place. But is this the real meaning of a traffic? By definition, traffic is the amount that pass through a certain place or travel in a certain way. In other words, the cars in the road are the real traffic. If there is only one car, then there is one traffic. And if there are more cars, there are more traffics. Throughout the discussion, imagine that one car is equal to one traffic load. Now, let us discuss how traffic engineering affects our cellular communication. Ideally, we want to provide one channel for each subscriber to make the communication have high availability. However, that would mean that if we have 1,000 users, then we will have 1,000 channels. Unless you want to say goodbye to high amount of money, this method is uneconomical. So, how do we address this problem? It's simple. Instead of allotting one channel to every other user, we will reduce the number of channels and offer only the remaining channels to users that need the channel at that particular time. In other words, we are allotting time slots to mobile subscribers. But what if the cellular communication providers runs out of channel to offer? That is where traffic engineering comes in. Traffic engineering will provide the probability that all of the subscribers will call at the same time, and from there, the engineers will determine how many channels will be provided.
Cellular Grade of Service. Grade of Service, or GOS, is a measure of probability that during a specified period of peak traffic, a call that was offered to a group of chunks of circuits will not be able to find an idle circuit at the first attempt of a call. GOS is usually applied to the BCR of traffic. Generally, GOS is measured by considering the traffic carried, traffic offered, and calculating the traffic blocked and lost. The measure of GOS is the proportion of lost calls. For cellular circuit groups, an acceptable GOS is 2%. A GOS that is equal to 2% means that 2 users of a group of 100 users will encounter a call refusal or blocking during the BCR at the end of the planning period. GOS can be calculated using the Erlang-B formula as a function of the number of channels required for the offered traffic intensity. The formula can be used to derive the number of lines needed when traffic in Erlangs during BCR and the desired GOS is known. The Erlang-B table is used to do so. So how do we use the Erlang-B table? First, let us introduce the different parts of the table and what does each value represent. The numerical column headings indicate blocking probability B or GOS in percent. The numerical row headings indicate the number of lines, trunks, servers or channels of the system, while the numbers in the middle of the table represent the value of traffic intensity expressed in Erlangs. Now, let's have an example in order for us to know how to use the Erlang-B table. Suppose that our desired system configuration can handle 9.010 Erlangs of traffic, and we desire a blocking probability of 2%. By looking at the value at the leftmost part of the table, we can therefore say that we need to establish 15 lines in order for our desired configuration to accommodate 9.010 Erlangs of traffic and obtain a grade of service of 2%. This traffic model is mostly used compared to the extended Erlang-B and Erlang-C model. In this formula, it is assumed that block calls are cleared immediately. Blocked calls that are cleared immediately means that the call that was blocked because the line was busy is not queued or retried, but instead vanishes forever. The blocking probability or grade of service can be calculated using the Erlang-B loss probability equation. The value for the blocking probability or GOS can be expressed in percentage by multiplying the result by 100. Looking at the formula, A is the traffic intensity expressed in Erlangs, while N is the number of trunks or lines offered by the system. Putting the formula into use, we will have an example. For our sample problem, let us calculate the blocking probability for a 5-channel cell with an offered traffic of 1.66 Erlangs. First, let us identify the given. For our traffic intensity, which is A, we will be using 1.66 Erlangs. While for the number of channels, which is N, we will be using 5 channels. Substituting the values to the Erlang-B loss probability equation will give us the following. Multiplying the result by 100 will give us a grade of service of 2%.
Ideally, one base station is needed in one cell coverage. However, as time passes by, more and more subscribers become present in a cell. Thus, more traffic is generated. And one base station may not be enough to accommodate all traffic loads. Hence, traffic engineers build more base stations in a cell area to accommodate the added traffics. As a result, the area coverage of a base station decreases. This method is called as cell splitting. To further explain cell splitting, imagine a wide road. All cars can freely pass one by one. But as cars continue to add up, the road will not be able to accommodate all of the cars. What if we paint a line in the middle of the road? There are two roads now available for cars, which mean more traffic can be accommodated. Aside from cell splitting, sectorization is another common practice to accommodate added traffic loads. Sectorization is done by replacing the omnidirectional antenna with 3 sector antennas of 120 degrees opening or 6 antennas with 60 degrees opening. The maximum traffic capacity of sectored antennas is greater than the omnidirectional antennas. Therefore, more traffic can be accommodated. Parameter that can affect the quality of service in a cellular network is the channel holding time. It is the time that a mobile station remains in the same cell during a call. Channel holding time is less than call holding time if the mobile station travels more than one cell. So, how is channel holding time related to traffic? Well, as channel holding time increases, the number of subscribers waiting for an available channel increases as well. Hence, more traffic is generated. In fact, the peak or average traffic in a given cellular network is equal to the number of subscribers multiplied by the average channel holding time. Let's have an example. From the following data, determine the average holding time of a cell. Maximum calls per hour in one cell is equal to 28,000. Blocking probability of 2%. Offered traffic is equal to 821 erlangs. We are given N is equals to 28,000 subscribers per hour. A is equal to 821 erlangs. And the blocking probability is equal to 0.02. We are required to find T, which is the average channel holding time. T is equal to 821 erlangs divided by 28,000 subscribers per hour. We can have 0.029321 hour. We will convert our answer into hours so that we can easily interpret it. Therefore, our answer is equal to 1.76 minutes. We have discussed all about traffic load. Now, let's study traffic capacity. By definition, traffic capacity is the maximum traffic per unit of time that a given telecommunication system or device can carry under specified conditions. As we all know, trains can only accommodate a fixed amount of passengers. Similarly, a telecommunication system can only handle a fixed amount of traffic capacity. Thus, traffic capacity is limited. If that's the case, then how can we increase traffic capacity? The answer is frequency reuse. For example, we have a group of cells with all using the same frequency. Then the bandwidth of the group of cells can only be utilized by few subscribers. Thus, drop calls are more likely to happen. But if we allocate frequencies to different cells, then the channel bandwidth can be optimized. However, we cannot use different frequencies on every cell since it will deplete the frequencies which can be allotted to other applications. Therefore, we limit our use of frequency by using co-channel reuse ratio. The CCRR enables us to limit the amount of reuse frequencies.
Let's have an example. A particular cellular telephone system consisting of 120 cells and catering 20,000 subscribers is using 12-cell repeating pattern. If each subscriber on this network uses his or her phone on average 45 minutes per day, and also on average 20 of those minutes are used during the peak hour, calculate the peak and average traffic for one cell, assuming callers are evenly distributed over the system. We are given N is equal to 20,000 subscribers, peak holding time is equal to 20 minutes, while average holding time is 45 minutes per day, and we have 120 cells. For our solution, 1 Erlang is equal to 1 channel R. Hence, to have our answer in Erlang, we need to convert the time given into R. Converting the peak holding time, we get 1/3 of an hour, while we multiply the number of subscribers in one cell, assuming equal distribution. Finally, we will have the peak traffic in one cell as 55.56 Erlangs. Similarly, to obtain the average traffic in a cell, we will convert the given into R and will obtain 1/32R. Multiplying the time to the number of subscribers, we will have 5.21 channel R or 5.21 Erlangs. Now, let us use our knowledge about cellular traffic engineering in a practical application. We will try to design a cellular network in Cebu City which has an area of 315 square kilometers. We will select a 3-sectored base station with K equals 1.95. Then, we limit the radius of each site to 3 kilometers. We compute the area covered by each site with the formula site area is equal to K, which is 1.95, multiplied to the square of the radius. We arrive with the answer 17.55 square kilometers per cell site. Computing for the required number of cell sites, we divide the total area by the site area, which is 315 square kilometers divided by 17.55 square kilometers. We arrive with an answer 18 cell sites. So far, we have these parameters. Hence, we plot each cell on the area. Next, we assume 37,385 subscribers and a holding time of 30 seconds. Now, we'll compute for the co-channel reuse ratio or CCR. To compute for the co-channel reuse ratio, using the number of cells, which is 18, we will have a value approximately equal to 7. Dividing the subscribers into each cell, assuming equal distribution, we have 2,077 subscribers per cell site. Finally, computing for the traffic, we convert the holding time into R and multiply it to the number of users per cell site. We get a traffic of 17.308 erlings. To get the number of needed channels, we used Erlang B table. The upper portion of the table corresponds to the value of freedom service, while the left side corresponds to the number of channels. First, we look for the 2% blocking probability since it is the acceptable value for cellular network. Then, under the 2%, we'll look for the value that is close to 17.308 erlangs, which is 17.51. Looking at the leftmost side of the table, we know that there should be at least 25 channels per cell site. Now, we have the summary of our cellular network design. In this problem, we just show you how traffic affects the cellular network design. Hence, other parameters such as transmit power and cell distance were excluded.